The antenna sticking out.
Cool. Okay, great. So for the last talk of the session, Matteo Busi from Università di Venezia, Ca' Foscari, will talk about obfuscating crypto code while preserving constant time. Take it away.
Thank you, Marco, for the introduction. I'll try to be fast because I'm standing between you and lunch. And, well, this is actually, hopefully this works. Yeah. This is actually started as a kind of side project, fun side project to learn more about coq/rock. And then it's quite interesting, so we submitted. It's still a work in progress, so I will tell you where something is not still finished. So let's start, and well, I had this slide because we presented this somewhere else and people were not secure compiler guys. So compilers, what's a compiler? A compiler is a function with, well, it's actually for us seen better as a composition of some transformations that map some source language into a target language. And we would be happy, very happy, if this compiler preserved some functional properties like correctness. So for instance, think of compsert, and non-functional properties like cryptographic constant time or hyperproperties, robust hyperproperties, whatever. So this is more or less the setting. And we started with a very narrow question. What if we take a single program transformation, actually a class of program transformations, and we proved that they preserve some property of interest? And for us, the choice was, well, maybe let's take a look at program transformations that are relatively simple to like formalize or to characterize, and which are not well studied. And the choice went into program obfuscations, which are actually well studied for correctness, well, some of them at least. But as far as we know, there's not much about their preservation of security properties. And the property of interest is cryptographic constant time. Again, this is very well studied. We have a lot of formalization to start from. And the idea of cryptographic constant time is to defend the program against some intruder that observes I/O operation of a program and its, let's say, running time, the time that takes for the program to perform some operation, for instance, cryptographic operations. And observing that behavior, an attacker can actually discover some secrets, for instance, keys. And sorry, I didn't tell you what a program obfuscation is, actually. It's like a program transformation that scrambles up your source code and actually changes the data flow or the control flow of the program, making it hard to reconstruct the original information. Actually, this is precisely stated in some sense that you can think of it as a program transformation that when you try to analyze the target program leads your analysis to reach top very fast. So in the abstract domain, it reaches top. This is a possible formalization of that. And you may wonder, well, I don't know, why should I obfuscate cryptographic code? Well, actually, we really don't know. It looked like a fun project, but it actually may have application to white box cryptography or the deployment on the web of programs like minification can be seen as a kind of obfuscation. So let's go ahead and let's see an example, which is pretty standard, which is mixed Boolean arithmetic. And that takes a program, which is this if then else, for instance, that has a few expressions like this comparison here and this assignment here, and that it obfuscated using this nice property of the plus operation that tells you that you can rewrite this plus operation as a combination of plus some bitwise operations. So for instance, this one can get transformed to this one, and this x plus y gets transformed in this way. This is actually there's actually a class of these rewriting rules, which is quite well understood for finite fields. And that's it. It may not be trivial that this is correct, but this is actually working for for integers, so finite fields. So we saw an example of an obfuscation. Let's see something a bit more concrete about cryptographic constant time. And the thing is that we consider there are a lot of different definitions for this property. We consider this definition, which is pretty much standard in an imperative setting, with an imperative language which is actually memory safe, with array and pointers, which is inspired by a core of Jasmine, which is a well-known programming language, well, for cryptographic code. And the cryptographic constant time is just another termination insensitive non-interference. And it tells us that if we take a program P, we run it on some low equivalent memories, and if this program terminates in both memories, then the leakage that the program produces is the same. So a bit more formally, we can write it like this. I don't want you to read all that, but the nice thing is about this leakage here that you can see. If both program terminates with some leakage L and L prime, then they end up having the same leakage. And this leakage is actually, well, I want to go into details, but that's a structured leakage in many cases. This is inspired from previous work in the literature at CCS'22, if I remember well. And L tracks down the operation that happens in P. So memory operation, which we call them memops, which are array and pointer location, but not their actual values. And the results of guards/condition evaluations for each, for instance, on if then else's and while. So that's more or less the setting. And now we can talk about preservation. You all know about preservation. So the preservation of this property here, which is cryptographic constant time, is just if P is cryptographic constant time, then its compiled counterpart, which I will never write the compiler, I just write the pink program, is CCT. There's a nice remark, which is, I guess, clear in this community, but apparently not everywhere. An obfuscation may actually increase the leakage, but since we are looking for a non-interference, we are just interested in comparing the leakage intra-language at the target level. So if they were the same at the source level, then they must be the same at the target level. But nothing guarantees us that at the target level the leakage is the same as the source, or is less than the source, whatever less means. So our idea, since particularly Pierpaolo is very fond of static analysis, was, well, can we do something statically to check that? So without relying on some semantic properties of the programs? And the answer is apparently yes. I will tell you in a while why apparently is the keyword here. And we need two additional definitions. So consider these two this program, which is as simple as an assignment to x to 0, and then an if then else, a generic if then else, with a guard and some comments. This gets obfuscated to this thing here, where the x equal to 0 gets obfuscated as a while loop that decreases x with some guards, decreases x up until x is 0. So this guard checks if x is 0 or not, and exit the loop. Here we would like to look at top-level expressions, which are circled here. It's kind of a strange definition, but for the sake of this talk, this is a top-level expression, x is not. G is a top-level expression. C1 and C2 are not expressions, so that's fine. G prime is an expression, G is an expression, and x minus 1 is an expression. And on top of that, we magically build this correspondence M, which maps, let's say, target level, top level expressions to their source level counterparts. So, yeah. So G is mapped back to G. X minus 1 is mapped to this star thing to denote that this is new. And the G prime the same. Of course, we don't actually notice that we don't actually use syntactic equality. I mean, this is a case, but we don't require syntactic equality because this is kind of more at the semantic level, and it depends a lot on the obfuscation. So That's where the, let's say, magic happens, and we will probably require this M to be generated by the obfuscation, but we don't know yet. So our preservation check is now ready to be revealed, and it goes as follows. It's very simple. If the correspondence, so the function that tells you the correspondence between the source and the target, tells you that the expression is new, this star, then we require that the memory operation of the expression is empty, or this expression, if this expression is a condition, we require it to be a tautology. Otherwise, if this is not new, we just require that the memory operations, the memops, are preserved across the transformation. And yeah, here is a big thing. Deciding if an expression is a tautology, of course, is hard. But often, since we know how this obfuscation is built, often we already know beforehand if this is a tautology or not. So this is kind of a trick. So our conjecture is the following. If P is CCT and it passes, and the obfuscation together with P passes our preservation check, the one that I just showed you, then its compiled version is CCT. And, well, we actually wanted to prove that in coq/roc. And I thought at the beginning this was like an afternoon task, but in the end, it was not. I'm working on it, still working on it. And this plus some additional reasoning on the form of the transformation tells us when a program obfuscation is safe to be used in any case. And this is actually very trivial. So if this transformation preserves CCT, if for any P this satisfies the preservation check. And, well, this is trivial, of course. And, well, so let's go back to Big's Boolean arithmetic. We have this example here. And as you can see here, these expressions, I maybe have, this box here and this box here correspond through M to this expression here and this expression here. And as you can see, the MBA never adds top-level expressions, because it's the way it is defined, and uses the obfuscated expressions, in the obfuscated expression, the same operands from before. It just changes the operations. So it adds no new memory operations, and so MBA is always secure. It satisfies the corollary from before. So we are very happy with that. But, of course, more, let's say, complex obfuscation do not preserve CCT. So, for instance, we have this anti-taint analysis from Tigris, which is an obfuscating source-to-source compiler. And it obfuscates the data using control flow, the example I showed you before. So this assignment here, an array in position 3 is assigned to 0, is obfuscated as this while loop. And, well, this new guard here has an non-empty memop. And since this is not empty, the check fails. And so CCT might not be preserved. This is a bit imprecise because actually this has to do with the fact that this is a while loop and not an if then else. Because if this was an if then else, this would be good, and we would have a false positive. But yeah, that's a static analysis, so that's okay. And however, what one can observe is that sometimes for the same obfuscation, we get secure programs. So we can go a program by program basis, and for those of you who know me, I love this translation validation stuff. So instead of doing that once and for all and doing like on every possible program, we do that program by program. And for instance, this is an example where the same transformation as before is secure because it never operates on memory, so this is trivially secure and no problem. So, concluding, we started with the idea, very simple idea, much less ambitious than previous talks, and of having one classes of program transformations and against one property of interest. And we show that a simple static check shows when an obfuscated program is still CCT. And if this check works for every program, then we have some suggestions, some guidelines. We can compile a list of transformations, obfuscations that are always applicable, so they are safe to apply, like MBA. However, if the check fails, we can still do something, and we can follow a translation validation approach and go case by case, and well, we are happy. In the future, we are, well, actually, yeah, in the future, because this should be the current working program, but I'm still stuck in the proof. So in the future, we would like to embed our static analysis in obfuscating compilers. Like we initially thought of Tigris and OMVLL, but some of the reviewers suggested LLVM obfuscator. So thank you, the reviewer, if you are here. And we are looking into that. And also maybe in the future, this could be very interesting to have more transformation and more properties to make the thing a bit more interesting also outside the specific fields like white box cryptography and stuff. And that's it. Thank you for listening. And of course, I'm happy to take any question.
Okay. Yeah, Yao.
Hi, thank you for the talk. And I have a question. I'm a little bit unsure. That is the instruction pointer IP is part of your leakage model, or it's not?
Wait a second. Not really, because we are at a higher level than like low-level languages. But in some sense, it is, because we track conditions on while loops and if-then else's. So you can reconstruct it. If you want to have an instruction pointer, then you should be able to do that, I guess.
And you can also apply obfuscation on it.
Sorry?
Can you also apply obfuscation on your IR accesses? Sorry, IP accesses? It's a random question.
I don't know. Actually, I guess. But yeah, you can, because this actually works. I didn't show here, but it actually works on control flow flattening, where you actually explicit your program counter. And so, yeah.
Yeah, I see. Thank you.
Another question there.
All right, thanks for the talk. So that might be a bit of a naive question, but the way I understand it, constant time programming is used against timing attacks, right? But from your definition, I don't see where the timing would come from, right?
Yeah.
It seems to me you're more doing an observational determinism kind of property. So how would that work? How would you give guarantees about timing?
Yeah, because this is not... Can you hear me? Yeah. This is a more of an abstract model of cryptographic constant time, where this is pretty standard in programming languages. There's a paper there are a few papers about that. But yeah, give me a second. Yeah, here, when you track memory operations and the conditions of loops, then this is I would say, an abstraction of what happens at low level with cycles. So you can reconstruct that information. Well, sorry, no, not exactly. This is an over-approximation, I guess, of what's happening at the low level with timings.
Okay, but just maybe as a concrete example, you have this obfuscation as a while loop, and if it's not memory dependent, you say it's trivially okay. The one with x equals 0 gets obfuscated.
This one.
Or the one that you had at the
at the end, right?
Exactly the next one. So this one you say is unsafe, right? But if you go to the next slide, right? In this case, let's say if x before had my secret key, right? Basically, the timing of how long the loop runs is going to leak information if I can measure that. Right?
Yes, but not in this model, because here x, you can think of it as a register, and in this model, well, yeah, I haven't shown you, but this is actually a non-interference, right? So here, X and like other names are, you can think of them as low parts of the state, and this is fine if you leak them.
But I mean, you can load like a secret from memory, and then it ends up in a register.
Yeah, but in that case, that wouldn't be good. I mean, if you swap this one, like X equal to A3, then you keep track of that.
Okay.
You can think of it. I mean, it's like a taint analysis for information flow. That's the same thing.
So like your obfuscator like does not allow secret conditions.
Yeah, exactly. Yeah, that's the typical cryptographic constant time policy that they use when they program cryptographic libraries. They don't care really about time, but they do care about this abstract model that allows you to say that there are no timing problems.
Thank you.
Any more questions? If not, let's thank Matteo again.